Okay, here's what I would call your basic differential equation free response. It's very, very likely that one of the six will be a differential equation. And by differential equation problem, I mean they're going to give you the derivative with respect to time or the derivative with respect to something written in this format, dw dt, dv dr, something like that, where something's changing because something else is changing. This is the temperature is changing over time. So you don't know the function that gives you the temperature at a particular time, but what you do know is a function that gives you the rate at which that temperature is changing over time. And apparently this is a thing that in real world applications is more often the case. You'll know about the rate at which something's changing more so than you know about exactly be able to predict the direct result of plug in a time and get out the actual temperature. Anyway, part A, we've got dw dt, 3 cosine t over 2w. W is measured in degrees Celsius and t is measured in hours. So dw dt would be like degrees per hour. At time t equals 0 hours, the temperature inside is 3. So there's your classic initial condition. So we have one data point that's actually on the curve of w as a function of t. So it says write the equation for the line tangent to the graph of y equals w of t at the point where t equals 0. So we don't know what wt is, but the function, some curvy kind of thing, obviously has some kind of trig aspect to it. But we know that there's a point on there at 0, 3, and then when it says use the equation to approximate the linear the temperature inside the refrigerator at 4/10 of an hour, we're going to use linear approximation there. And that idea is that if you have a curve doing something crazy, and you have a point on that curve, the tangent line can be used to approximate values on the actual curve as long as you stay close to your point of tangency. So in other words, if this is t equals 0 here, well, I don't know why it would be over there and not on the y-axis, but give me a break. We're trying to approximate what's going to happen on the red curve at t equals 0.4. Well, what we're going to do is get the y value at on the tangent line at t equals 0.4, which will be really easy to get. So this is a while back in the year that we did linear approximation, but it's a pretty simple concept. First thing we do is write the equation for the line tangent to the graph. So we need a slope, and we need a point, and it's at t equals 0. Well, they gave us the point at t equals 0. The temperature is 3, so we have the point 0, 3. How do you get the slope? We get the slope, the instantaneous slope from the derivative. So we're going to get the slope by plugging in t equals 0 into this thing. Oh, and of course, we're going to need the y value as well. So the slope is going to be 3 cosine of the t value, which is 0, over 2 times w, which is the y value, if you will, 3. Now the cosine of 0, of course, is 1. So we get 3 over 6, which of course is 1/2. So there's our slope. So the equation of our tangent line is y minus our y value, which is an m times x minus our x value. So if you wanted to write it specifically, so it's a little bit more useful, plus 3, then you realize, wow, that 0 is kind of silly there. So 1/2 of x plus 3. Back in the day when we did this in class, we called this L of x equals 1/2 of x plus 3. But I think you could suffice to say y equals 1/2 of x plus 3. And remember, that's the equation of this blue tangent line. Now, use that equation to approximate the temperature at t equals 0.4. Well, I have a major issue here. I used x's instead of t's. I should go back and change those to all t's. Okay, that's sloppy. So let's put t minus 4t minus 0. T, L of t, 1/2 of that. So y of 0.4 is 1/2 of 0.4 plus 3. 1/2 of 0.4, of course, is 0.2. So it's going to be 3.2. So that's the approximation of the y value on the curve when the time is 4/10 of an hour. Okay, so on to part B. Find the particular solution of this thing to the differential equation with the initial condition that w of 0 equals 3. So in other words, that's the point that they gave us back here in the original thing. All right, so we had a little experience with this back in the day. We know that w changes with respect to time according to 3 cosine t over 2w. Big thing here is that in order to figure out what w is, because that's what they want us to get, is what does w equal in terms of t, you have to get the w's with the w's and the t's with the t's. That's referred to as the separation of variables. And in these problems, inevitably, if you do not do that, when they ask you for a particular solution, you are going to get 0 points on this section. This is usually the big section. This might be worth 4 or 5 points. So, of the 9. So, all you're going to have to do to separate the variables in these problems is cross multiply. So 2w times dw, 2w dw is equal to 3 cosine t dt. And that looks good. If you want, we could divide 2 on both sides or something like that. But essentially what we're going to just do now is integrate both sides. And so we can integrate, and the integral of w with respect to w is w squared over 2. But since we have a 2 out here in front, that's just going to give us w squared. The integral of cosine is sine, because the derivative of sine is cosine. So the right side is just going to give us 3 sine t. But this is where we got to remember this is sort of an indefinite integral situation. So we have to add a constant of integration. Now, you might think, well, why didn't we do that on the left side? Why didn't we add a plus c over here? Well, if you add a constant to one side and add a constant to the other side, couldn't you just subtract the constant from the left side over to the right and get some new constant? So you only have to add a constant to one side, and that kind of incorporates any constant that could be there. So if you want to make things easy, we haven't quite solved for w yet because we have this missing constant, and of course it's w squared, not w. But we could go ahead and plug in our initial condition now, and our initial condition, of course, is that we have when t is 0, w is 3. So 3 squared equals 3 times the sine of 0 plus c. So, of course, 9 equals c, because the sine of 0 is 0. So, going back to this equation, we can now write w squared equals 3 sine t plus 9. So, solving for w, we get the square root of 3 sine t plus 9. Now, you may say, why didn't you do plus or minus? You're a calc teacher. You should know that whenever you take square roots of both sides, you have to choose, you have to use plus or minus. Well, we know, according to this particular solution, that we got the positive root of this thing. We got positive 3, not negative 3. Now, had the initial condition been w of 0 equals negative 3, we would have had to chosen the opposite of the square root, so that when t is 0, we would have gotten negative 3 as our answer. But we didn't get that, so we can take that negative sign away. So there's our answer for this guy. W equals the square root of the quantity 3 sine t plus 9. All right, part C of this problem. This is a little tricky, and you might be a little freaked out by it because it involves kind of incorporating what we've done before with this new information about the temperature in the kitchen is 20 degrees. And so you got a 20-degree kitchen, and then you got this fridge working inside that's trying to keep stuff cold. And the last, the 2 parts of the problem prior to this have been about this fridge and how the temperature in there is varying according to that dw dt thing, where it was sinusoidal, had a cosine in it and stuff. So what is going on here is there's a battle between the outside temperature and the inside temperature, the temperature in the kitchen versus what's going on in the fridge. And it kind of makes sense. If it's really hot in the kitchen, the fridge is going to have to work harder to keep stuff cold. So what we have is that the difference between these temperatures, in other words, it says for each degree that the temperature in the kitchen exceeds the temperature inside the refrigerator. So let's say it's 17 degrees Celsius inside the fridge. Well, that would be the difference of 3, because it's 17 inside and it's 20 outside, so the difference would be 3. You'd have to pay, what is that, 1/1000th of a dollar, so that's like a tenth of a cent, right? For that degree, for those 3 degrees. So it would be 1,000th of a dollar times 3 would be 3,000ths of a dollar. However, that temperature is going to be changing and stuff that entire time, so we want to kind of capture all of the temperature differences that we have in there over those 24 hours and multiply them by that 1,000th of a dollar. So what we want to do is capture all of those temperature differences. So from 0 hours to 24 hours, we want to find out, we want to gather what all those temperature differences are. So our W of T is those temperature differences, because if you go back to that problem, it's like, or I'm sorry, the WT isn't the temperature difference, the W is the temperature inside the fridge. So 20 minus WT is going to be the difference between the kitchen temperature and the temperature inside the fridge. So we have to pay for all of this at that rate of 1,000th of a dollar. 1,000th of a dollar per hour. So let's put a DT on this guy and put a 0.001 on the outside of that thing. So now all of those degrees of difference in temperature are going to be accumulating from 0 to 24 hours. Every infinitesimal change in temperature or discrepancy in the temperature between the outside in the kitchen and the inside of the fridge is going to be accounted for in that. So if you wanted to, we could put our WT function in there. I think we probably should do that. So 0 to 24 of 20 minus, what was it? It was something like the square root of, I don't know, it was on the previous page, something plus 9. It was like 3 cosine plus 9 maybe, 3 sine plus 9. I don't know, I don't remember. I think it was 3 sine of t plus 9. I hope so anyway. But there you go. That's really, and that's all it's asking for, right? But do not evaluate an expression that would find the cost over the 24 hours. So we had to kind of gather up all of the incremental discrepancies in the outside temperature and the inside temperature, which this interval does, and then multiply it by 0.001. So this is like dollars per hour. And dollars per hour. And for each degree. So it's like dollars per hour per degree. And then this is going to be degrees. So that is going to get you dollars, basically, because when you integrate degrees per hour over hours, you're going to get degrees. So hopefully that helps you. Again, that one's pretty tricky because you have to really think about what are you multiplying this 0.001 by. Anyway, there you go. There's number 5.